Hello everyone, Anton here. Welcome to the third part of the Generative Modeling in Grasshopper series. This series is part of the course Computational Design Basics offered by the Digital Design Unit at the Technical University of Darmstadt. In this video, we're going to build a custom interface to sort and browse through thousands of generated design options. We'll be building on the parametric tower model that we created in part 1 and part 2 of this series. So if you want to follow along, make sure to watch those first. I'll put a link in the description below. Now, to benefit from generative design in your workflow, you need a way to browse and sort through all the options that your generative model created for you. This process is called optioneering, from options and engineering. Okay, let's get started from where we left off in the previous video. We have a model that's based on the Sears Tower in Chicago, and we are generating a couple of thousand options for that model, varying the heights of the 9 tubes that this tower consists of. So first of all, let's do a little bit of tidying up here. I'm going to copy and duplicate the model from last video, and I'm going to disable the previous one. Okay, so that would be our part 3, Optioneering Interface UI. Okay, let's review the model first. Here we have the generative part, which creates all the possible combinations for the 3 types of heights we want to have in each tube, in each of the 9 tubes. So we have heights of 30, 60 and 90, and this creates all the possible combinations for us for the 9 tubes. Then it gets sorted, finds the highest so that it can be used for the core. Then we switch to generating the tower model using meshes so that we can speed up our definition. Here's the old way we generated it. Yeah, it's easier. It's few components only, but this way it's faster. And then we are measuring the area of all these options entirely by numbers. We don't need a model for that. And we're actually using the area to filter or pre-filter from these 6,500 options that we currently have, only the ones that are above a certain total area. And actually here's the first thing that I noticed I forgot to address, is that once we filter the buildings based on the area, we all in the same way we need to apply the same filter to the areas, so that this is the filter. Basically, if the area is smaller than something, then we filter the building out. So we need to apply the same filter to all the areas and use those from now on, so that we have a correct match. So where do we have an area? We have an area here in our display tag, those tags that are displaying here, and basically that's where the mismatch is happening at the moment. So I'm going to, this is our new filtered areas. Is there a faster way to do that instead of reconnecting? Yeah, I can actually connect these ones here, these ones here, and then this would be the filtered area. So it gets used from now on, and yeah, also in the text box. So here we have only the filtered areas. Okay, we fixed that. Then let's improve the display a little bit of these options. So let's use black for the labels. Here in the text tag we have an input for the color, so I'm going to use a color swatch, set it to black, accept, and use that one here. So this text is black. And then let's also apply a custom preview on our towers. I'm going to, so these are our towers, custom preview. Here we go. We want to apply that here, and the color we're going to use for that comes also with a color swatch. And let's use a blue color, something like this. Yeah, that should do it. Here we go, and we can actually disable then the preview of the geometry before that. And then same for the shadows. Let's also do a custom preview for the shadows. The shadows are outlines, however. So the first thing we're going to do is to do boundary surfaces. So we have a surface for the shadow. Here we go, and then custom preview and use something a little bit darker. Here we are. Disable the preview of the other ones. Okay, so we have a slightly better preview. We could also hide this grid. We know that the grid is here. We can also hide the grid. Preview off. There we go. A matrix of towers in blue. So now we see a bit more clearly how the design of each tower looks like. So let's move on to sorting them first. And let me make a bit of space here. We can use the sorting component. Here we go. And let's bring in all the parameters so that we have them nice and ordered closer to us. So that would be the park shadow, that would be the neighboring shadow, and here we have the total area of the shadow, and we only need the floor area. Okay, we want to be sorting based on the area. The sorting component provides a way to sort a list, but also synchronously sort another list in the same way. Our key value will be the area, and in A we're going to connect the geometry of all the buildings. So let's go and bring in the geometries as well. We have them grouped over there. Okay, let's take this one and remove it from the group. So we're going to sort the designs. Okay, but we also need to sort then in the same way all the other corresponding values. So we need to sort the shadow area, the park shadow, and the neighboring shadow. Okay, so now what's left is to hook up all the sorted lists into our display interface, which is where we display the solutions on the grid. So let's bring that closer. Instead of the options coming in directly, we're going to use the sorted option. Then we're going to, we need to sort the shadows as well. This is our shadow. Let's take it. So everything that belongs to the building needs to be sorted synchronously. In E we find the shadows. Okay, so this is the shadow, comes in here, and here we have the floor area first, which comes from the key parameter. Then we have the shadow area, which comes from B. Then we have the park shadow, which comes from C. And then we have the neighboring shadow, which comes from D. Here we go. So as you see, now we have a problem. Okay, this doesn't seem to be working, and let's figure out what the reason is. Why I know it's not working is because we lost the numbers here in the labels, and also we're seeing always the same tower design. The problem lies in the structure of the data and not the data. What's coming in here from the objects is a tree of 45 branches. Here, however, it comes a tree of 6,500 branches. It's not been cleaned in the area. And if we check everything else, it's also a tree of 45 branches. So we need to go back, and at the beginning of this video we filter the area, but we forgot to clean the tree. This is happening here. So we filter the area the same way we filtered the heights for the designs, but we forgot to use the clean tree component. And let's just use it now. This is the tree we want to clean, and pass that to the area. As you see, that already fixes the problem. Let's stop the preview of this mesh here, which is to be found here and here. Okay, there is one more thing wrong with our component here, and that is that what comes in the sorting key is a tree of 45 branches, and each branch has only one item. So basically no sorting is happening. We need to flatten that into a list of 45 values, sort that, and then graphed it later on, since most of our components are using trees, at least this one here. Just to avoid overloading the definition with cross-matching trees and lists, I will lock the solver. That would prevent the calculation of the definition every time we connect a new wire or we change parameter. So I'm going to flatten the area and all the corresponding values that come in this sorting component. That way what comes in here is now a list of 45 values. And then let's see what we need on the other side. We need to graft the area here, since we need a tree. We don't need to graft it because we're anyway flattening it over here. We need to graft this one because it goes down. Whatever comes in here, we need to graft it. We need to graft this one as well, and this one. And this one can stay like that, because it's also coming in here where we are flattening it, so it doesn't hurt if it's already flattened. Now let's re-enable the solver and see what we're getting here. Well, first of all, to check, yeah, 45 values in a list are coming now, and then everything should be sorted. But the way that sorting works is that the smallest will be on top and the highest on the bottom of the list. Let's preview that in a panel. The first one is 396,000, and the last one, yeah, 428,000. So if we want the largest area to be shown in this first location, and then everything else should be smaller, gradually smaller, then we need to reverse all these lists. Again, I will stop the solver and reverse the lists. There we go. Enable the solver again. And now we see already that the largest area, which is the full tower, all tubes are the maximum height, is at the first location, and then it goes gradually decreasing from there. By the way, I'm going to switch here to shaded mode from Arctic, because that would speed up our preview a bit. Yeah, way faster. And then we can switch to Arctic modes only for screenshots and so on. So this is way more responsive, and we can work like this. If we want to sort, for example, on the area of the shadow that the building casts over the park, for example, then we want the smallest, so then we don't need to reverse the lists. So let's group the sorting logic into its own group, so we can later on easily change how we want to sort things. I'm going to exclude that in the group and make it part of the other group, because instead of connecting 4 wires, we then need to connect only 1 wire. That would be the it's a number or integer. That would be the values that are connected here, so let's include that into the group. Values, total area, the shadow area, and so on. And then let's include that here. So we don't need a panel. That would be our sort by floor area group. I'm going to duplicate it and quickly rewire it so we can sort by park shadow. Actually, there is maybe a better way to do that. We can tidy this up a bit and also be more explicit at which wire carries which information. So let's start with the sort by floor area. Here we have geometry, which is the geometry of our building. This is the shadow shape, and this is the geometry. So let's connect that here, and that goes in here. And then we have the area, we have the shadow area, park shadow, shadow shape. So I'm going to copy all these and use them on the other end of this component. Let's move it here. Let's make space for one more parameter here, and we'll see why. I'm gonna also flatten this output and reverse this one. So let's connect everything in order. Geometry goes in A, area goes in B, shadow area goes in C, park shadow goes in D, neighboring shadow goes in E, and the shadow shape goes in F. And then on the other hand, let's do the same. Geometry comes out of A, area comes out of B, shadow area comes out of C, park shadow D, neighboring shadow E, and the shadow shape comes out of F. Now here, this is actually our component we connect to the labels interface. Floor area is first. Floor area is first. Then comes in shadow area. I'm looking here. Then comes the park shadow, and then comes the neighboring shadow. So let's graph this as well. The advantage of what we just did is that now I can change the sorting criteria. Let's say I can sort by shadow, and I don't have to reconnect anything here. So let's call this component actually sort reverse, and then let's duplicate it and drop that one here, delete that one here, duplicate this one, and we'll call that simply sort, and switch off all the reverse. So we have now one group where we can sort largest first. Let's say if we want to find the largest floor area, and we have one group where we can sort smallest first, where we can find, for example, the smallest park overshadowing. So we're still gonna make the park shadow the key component here and connect that to our definition. And now we will see that the building that's here is the one that has the smallest shadow over the park, and visually it also looks like that. Okay, next we're going to build the optioneering interface, which would give us more granular control over what options we filter out and what options we keep. So we can filter based on all the 5 parameters instead of simply sorting on one of them. So in building the interface for browsing the options, we will need a couple of axes for each of the evaluating criteria we have, for the floor area, for the shadow area, for the shadow over the park, for the shadow over the neighbor, and so on. So we need access for those. Then we can place a point on that representing the value for a given design, connected with the point from the same design on the other axis, let's say on the floor area, and then connected to the point on the shadow area axis, and so on. So we'll have a line representing each design options on these axes. And we'll start by building the axis first in Grasshopper, and then display the bounds in which they are, what's the minimum, what's the maximum value on this criteria, and then displaying all the solutions. And then we'll move on to building a set of sliders which help us navigate and kind of squeeze a certain axis in, so only the options within a given range are remaining. So let's start by building the axis. Those would be lines, and I would place them somewhere here below our matrix. The line component we're going to use is SDL, line from a starting point, a direction, and a length. We can bring in the Y vector and set it to 250, and then we'll use the expression editor here to -x. So that would be the starting point, and then the direction will be the same, and also the length will be 250. So here we have the first line. It starts 250 units down from the 0, and it's 250 units long. And then how many lines do we have? 5 parameters, which means 5 lines. Let's hard code it for now. 5 lines. So we are going to move this line along the X 5 times. So let's create a series that starts from 0. The step will be 250, the count will be 5, and this will give us the x coordinates, so to say, of these lines that we want. We can pass them to unit x vector, so that we can use this vector to move, and then we can move the line we have with this vector. So here we have 5 lines to display our solutions on. Next, let's label the lines. For that purposes, we're going to take a text 3D tag, 3D text. Yeah. The location, let's label them slightly up from their starting point. So first let's find the endpoints of these lines. Here they are. And slightly up from the starting point would mean that we want to move along the y direction with maybe 50 units. Move this point, the starting point, and that's the location for our text. What the text will say, we need now 5 times, so I'm going to bring in a panel, switch off the multi-line data, and type what we want first. Let's go with the floor area first, then we're going to display the shadow area, then we're going to display the park overshadowing, and then the neighbor overshadowing. So we actually have 4 lines, so let's fix that here. 4. There we go. And that should display it. Let's use a size of 15. I think it's okay. There we go, and let's center that on the line. So in Justify, I'm going to use bottom center. Okay, we have the axis, and next let's display the bounds of each of the axes. So what's the minimum floor area, what's the maximum floor area, what's the minimum shadow area, and what's the maximum shadow area, for example. Take these, they are the sorted ones, and flatten each one of them. So we can use them to display the bounds on the axis here. We can do 4 times the same thing. 1 for the area, find the bounds, display them, then copy the same thing and do find the bounds, shadow area, and so on. But instead of that, I'm going to use the power of trees in Grasshopper, and I'm going to entwine all of these values into one tree with 4 branches. So entwine is the component we need, and we're going to connect these lists into these addresses here. These are path addresses. Now we have one tree with 4 branches, each branch for one of the criteria. And then we can find the bounds, and what it will give us is a panel to see. It will give us the minimum and maximum floor area, the minimum and maximum shadow area, park overshadowing, and neighbor overshadowing. Okay, now we can use these and display them. Deconstruct the domain. So now we have the starting point, the starting value of the domain here, and the ending value of the domain here. We're going to use again tag. We're going to use the starting point, this time directly, and the label will be this, but we need to flatten it because the locations are coming in as a list. Let's justify bottom right. We're going to need another label, and then flatten the output on the end and display that at the end point. So we have starting, minimum floor area, maximum floor area, and for each axis we have the same. Good, now we are ready to display all the design options on these axes. To do that, we're going to also use this tree here, and we're also going to use the concept of evaluating a curve using the t parameter. So if we reparameterize the lines we created, which come in here, let's call them axes. So these are our axes. Let's use them here. So these are our axes. If we reparameterize them, then we can place points on them using the t parameter in the range of 0 to 1. However, our parameters are coming in all kinds of ranges, so let's remap those. Let's remap the numbers that are coming in from here to a domain that is coming in from the bounds, and the target domain is 0 to 1. So now we remap them, and then we can do evaluate curve. The curve will be our axis. Let's graph this so it matches the structure that we're getting from here. 4 paths, 4 branches, and those are our parameters. We have 45 points. So here we have more or less 3 spots where all the solutions lie. And the shadow area we have high variety, and then in the park overshadowing we have 2 options, and the neighbor overshadowing we have 3 options where all our solutions lie. But let's first draw the polyline that connects each value for the corresponding solution. So polyline is drawn between points. However, if I connect this directly like that, the polyline will be drawn on each axis. This is because the way we've structured the data here is for each axis all the 45 options. What we need to do now is to flip this so that we have for all the 45 options the 4 axes. And this is done with the component flip matrix. See what happens now. If I connect this, in the input we have 4 branches with 45 items, and in the output we have 45 branches with 4 items in the list. And now, as you can see, here we have all the curves. Each one of them is representing a design option. Okay, so we have the curves. They are here, and we can hide the preview of everything else. And now we need to begin filter based on those. To build the filtering interface, we're going to use sliders for the minimum range and for the maximum range. So let's start with sliders for the minimum range. Since we already reparameterized the curves, our slider will go from 0 to 1. So let's do a couple of sliders here. We need 4 sliders for the minimum and 4 sliders for the maximum of the range. Okay, and then let's merge them into one list, and let's evaluate the lines with these sliders. So evaluate curve. This is the value we want to evaluate on, and these are the curves. So I'll call this minimum and maximum. There we go. So that is our maximum. Now let's display the value for each of these that corresponds to the actual floor area, shadow area, whatever. To display the value, we are going to use another text tag. The location will be the point we are getting on the curve. The size will be the same. The justification will be on the other side, middle left. So it's really on the point. So to get the text for each of these tags, we need to find the corresponding value. And we basically need to do the reverse remapping. Here we remapped from the space of the values into the space of the curves, from the bounds to 0 to 1. Here we need to do the opposite. Since our sliders are in the space of the curve from 0 to 1, we need to remap those back into the space of the values. So I'm going to bring in a remap component again. The value comes in from here. The source domain is from 0 to 1, which is also the domain of our sliders or the curve, and then the target domain comes in from the bounds. But since that is a tree, over here we need to flatten it. Flatten. So now we've remapped our values, and we see that they are not whole numbers here. So let's pass them to an integer component just to make them integers, and then that's the text. Actually, too close to the axis, maybe we can improve it by concatenating an arrow before that. So I'm going to bring in a panel with an arrow and a space behind it in here. So that's the less than sign, and that would be our text. Yeah, this is a bit better. We can maybe add more space behind the arrow. There you go, maybe even some space before the arrow, so that this is not on the point. There we go, this looks good. And we need to do the same for the other tag. So that would be copy paste, and the locations are coming from here, the values are coming from here, the domains stay the same, and we just need different slider values. There you go, this is the maximum. Maybe we can also do minimum, so we know what's what, and maximum. There we go. Something's wrong here. Let's see why. I backed them with a shortcut. Okay, so let's go to Rhino and just undo the last command, which would be the bake. Okay, that's the reason. Then let's preview that again. Okay, there you go. Now we have the sliders, and what's left to do is to do the filtering. Since we already have the values on which to filter and the values to filter, that should not be that difficult. So let's do that next. Let's just get the values first. The remapped values are here. So these are the remapped values. Let's call them remapped values. Make sure to get a number this time and not an integer, because those are between 0 and 1, so they are not whole numbers. So these are our remapped values, and we want to check if they are smaller than our minimum. So if this number is smaller or equal to our minimum, and what I see here is probably that we need to graph those, so that would be our minimum sliders, minimum values. Let's graph this to match the structure that comes in from the remapped values. So if they are smaller or equal to, actually it's the opposite way around. We want to keep the values only if they are larger than the minimum values. So let's do that, and then larger. So we want to keep these values only if they are larger than these values, and let's call this maximum values, maximum values, and reconnect them to the maximum values actually. And we want to keep the values only if they are smaller than the maximum values. So how do we check that? At the end we're going to use a call pattern, but let's first build the pattern. Let's see what it gives us. Okay, it gives us a list of false and true for each of the value. We need to flip the matrix, so we're working only with the values for a particular solution. That would be flip matrix. At the moment we have all the floor areas in one list for all the solutions. What we want to get is for one solution the area, the shadow area, and the neighbor and the park area. So we want to flip the matrix, and then here's what we get. So for this solution we have 3 falses and 1 true. So since we have falses, we want to skip that solution. we want to keep only solutions where all the 4 values are true. And in order to do that, we can use mass multiplication. False and true are treated as 0 and 1, and if we multiply them, then we'll get 0. Even if one of them is false, we'll get 0, and only, like in this case here, and only if all of them are true, we'll get 1. So that would be the first step. We need to do the same with the other one. I'm using the larger, let's go for larger or equal, smaller or equal. So here we have the same, and then we also want to multiply these 2 filters. So multiply, again, they both need to be 1 in order to keep the solution. And that's our pattern. And now we need to get the shapes and apply that filter before the display. So let's make some space here. We need to apply that filter to what we are displaying. So here we are. What do we need to filter? What comes in here? Basically everything. So we need to take one of these things, copy it, and use it somewhere here, fill it with information somewhere here. Okay, so this is the pattern with which we are culling, and we need to cull all of these lists and pass them over. So the geometry, let's graft it so it's branches in and not lists. And then we need this one, this one, this one, this one, this one. There you go. The pattern stays the same. We're culling the area, culling the shadow area, culling the park area, culling the neighbor area, culling the shape. Then these go in here. So now everything is reconnected. This we can use in our, so this is our new geometry. Let's call that geometry. And this is our new shadow shape, the filtered ones, shadow shape. Okay, and then we want to connect that to our display interface. So let's bring that a bit closer here and hook it up. This comes in here, the shadow goes into the shadow, and the geometry goes into the geometry. At the moment we have nothing to be displayed. We want to do one more culling, and that's the curves, so that we know how many solutions are left. So that would be this list, preview off, and this is empty, which means we need to play with the sliders a bit. So let's set everything to 0, and then let's set everything here to maximum. Now we have everything we had before, and let's say I want the minimum shadow, so I'm gonna move the maximum slider here and be left with only one design. Again, for some reason something is being displayed here, so I'm going to just select that. No, I'm going to select that and preview off. Also this one, preview off. This one, preview off. And here, let's preview off all of these. Okay, this is the design which has the minimum shadow over the neighbor. The shadows are also displayed somewhere here. Preview off. And this is its shadow. The numbers are not working. Okay, interesting. So the numbers are not working. The reason is that if nothing is passed over here, it's still generating these empty labels. So we need to clean the tree before that. Clean this tree, from the empty branches. Pass it over here, there you go, and move that into the group. Okay, we have this interface. Now let's tidy it up a bit, also to recap what does what. Here in this first group, we are displaying the axis labels. So axis labels. Move that aside. Here we have the maximum and minimum values. So that would be maximum, max and min values on the axis labels. And here we are actually drawing the lines for all the options. Lines for options or polylines. Here we are, we don't need that. Here we are displaying the labels for the minimum slider. Labels minimum, min sliders. And here we are displaying the labels for the maximum sliders. Labels max sliders. And what we do here is doing the filtering. So that would do the filtering. Actually, that whole part does the filtering. So let's bring those into the group as well. So that is filter. Filter with sliders. Okay, and these are the lines, so that should go in here. So we're sorting here based on one of the values we want, and then we filter based on everything else all together here. One thing to do is to actually increase the number of options we are reviewing. And at the moment we are shrinking the choice by filtering based on area down to 45 options out of 6,500. So I'm going to set this to 250,000, and let's see if my computer will be able to calculate all the options that are left. Okay, it finally calculated. It took 5 or 10 minutes, and as you see, we have way more design options now being displayed in our Optioneering interface. What I thought to do also is to walk with you together into the definition and see what took the most time and find maybe spots where we can optimize the definition. So if we start looking around with the profiler on, the profiler is switched on from here, canvas widgets, and then profiler. Then we can see that actually the generating of all the 3D models didn't take that much time, at 2.8 seconds, so that's pretty fast. Let's see then what actually took time. Here we have something. This is 3.6 seconds just to pass a value from here to here. This is actually quite slow. So why is that? This is converting probably. Yeah, probably it's converting numbers into, yeah, it's converting these texts into numbers here. So we kind of need that, so let's leave that here, 3.6 seconds. Then what else? The shadows, yeah, as we could expect, they take quite a long time, 33 seconds and then 34 seconds for unioning all the individual regions. Let's keep browsing here. So we have 8 seconds for the intersection, that's okay. And moving on to our sorting part, this is pretty fast, everything is in the milliseconds area. And then here we have still everything in milliseconds. Yeah, and here we have something. Here we have this shadow shape, just passing the parameter again, 12.2 seconds. What comes in is a curve, but what we have out is a geometry. So if we pass a curve again, maybe that conversion would not need to happen, and that could speed this up. So let's mark this for later. I don't want to connect anything. I have the lock of the solver on, because if I reconnect everything else after that wire will lose the profiler values. Okay, again here we see that conversion back from geometry to a curve, another 12 seconds lost. So that would definitely fix this. And that's it. Basically these are the weak spots, so that curve here. So let's connect this shadow shape and use that instead of the curve. And let's see if, so let's delete that and move it into the group. Let's do something like 3020 here, 320,000, and let's see how long it takes to calculate this time. Okay, that was way faster. Is this slow again? No, that's pretty fast. Super. Okay, so let's browse a bit what kind of options we have here. Thank you for watching, and see you in the next part, where I'm going to show you how to use the optioneering workflow to select designs based on different metrics.